Okay, good morning, everyone. Welcome to today's Consciousness Club. This is the last one of term before the summer break. We'll resume again in late September. So it's a real pleasure today to be hosting Chen Song. I've known Chen a long time, back when we were both studying in Queen Square. So Chen did her PhD at the Institute of Cognitive Neuroscience at UCL together with Geraint Rees. She then went off to do a postdoc in Wisconsin with Julia Tononi, and then she came back to the UK to start her own lab at Kubrick, the Cardiff University Brain Research Imaging Centre, in 2017. And Chen now leads the Brain Complexity Lab, investigating how the structure of the brain differs across individuals, looking into individual differences in brain function and conscious experience, and also looking at how this intersects with sleep, which is a really exciting and interesting area of research. So that's it. That's the introduction, Chen. The floor is yours. Thanks so much for joining us. Thanks so much for giving this talk.
All right, thank you. Thank you very much, Steve, for the nice introduction. And so for the talk today, I would like to show some of our recent findings from a very long project, which we have been doing for nearly 5 years now, looking into how sleep deprivation influences our brain structure, brain function, and then through that influence our conscious experience. And let me see if it works. Okay, so I would like to begin this talk with a question. Do you get enough sleep? I think it's fair to say that we are currently living in this age of sleep deprivation, where most people, at least a half of the people, are not getting the sleep they needed. And this is a map from CDC in United States. It's showing the severity of sleep deprivation across different states in the United States. And as you can see here, nearly a half of the people in the East and the West Coast are not getting enough sleep. And even in the middle part of the United States, like typically 1/3 of people are having less than 7 hours of sleep per day. And the reason why we are not having enough sleep partially is because we are not taking sleep very seriously. And that is also because we still don't know the real function of sleep, and the sleep to a large degree remain as a mystery. So sleep occupies about 1/3 of our life, and it clearly represents a significant opportunity cost. This is because every hour we spend asleep could be an hour that we spend doing something which may be more productive. Yet, paradoxically, sleep might be one of the most productive things that we ever do. This is because without sleep, nearly every aspect of our life is compromised. It's not just in cognition, in brain, but also in immune function, in heart function, in muscle, and in my risk diabetes. It's basically the sleep is modulating the entire biological system. To a large degree, sleep is almost like air and water that is absolutely essential to life, without which we may either be dying or make us easier to die. Although sleep is clearly essential, but its precise function is still unclear. That is both in terms of the benefits it offers and also the consequence of its absence. And these two, the benefits and the consequence of its absence, they are not necessarily identical. It's not that the sleep deprivation equals to just not having sleep. It may also have its own negative consequence on the brain and the behavior, cognition, and consciousness. Although we have been looking a lot into how sleep deprivation influences behavior and cognition, its influence on consciousness itself is in fact largely unclear. And to a large degree, compared to our research on the sleeping brain, our research on the sleep-deprived brain is much needed. It's much less explored. This paper, which was a review paper from 2018, it has done a systematic review into the topic sleep deprivation and consciousness. And this meta-analysis paper identified only 21 studies which have looked into the relationship between sleep deprivation and consciousness. And these studies mostly just use phenomenological measures of consciousness, and they don't even include measures of brain structure or function. So we still don't know these fundamental questions. Is the sleep-deprived brain structurally distinct from the well-rested brain? If so, does this structural difference lead the brain to function in a qualitatively different way, or it's just a degraded version of the same system? And how do these structural and functional changes give rise to altered conscious experience? All these questions remain unclear. So we don't know to what extent do the brain and consciousness adapt or maybe fail to adapt in the absence of sleep. And this is why we propose the hypothesis that we think a well-rested brain is able to maintain a delicate balance. This involves sustaining a rich internal world of conscious experience while keeping connected and responsive to the external world. So this balance depends on two key pathways. One is the cortical-cortical connection, and the other is thalamocortical connection. The cortical-cortical connection shapes the intrinsic dynamic of cortical activity and ensure that conscious experience is intrinsically rich, while the thalamocortical connection is making sure that this cortical connectivity is not just internally driven, but also aligned with the external sensory stimuli we receive from the environment, such that our conscious experience can keep aligned with the external world. And we know that during dream sleep, we still have the cortical-cortical connections active, the cortical-cortical interactions unimpaired, although the thalamocortical connections is impaired. So the dream sleep indicates that consciousness fundamentally is not about the connection with the external world or not about being responsive or encoding the external world, but fundamentally about the internally generated experience driven by the cortical-cortical connection. So we hypothesized that although these two pathways are balanced during in a well-rested brain during sleep deprivation, it is possible that this balance is lost, and this can occur in two ways. Either the thalamocortical interaction is weakened, but the cortical-cortical dynamics is intact. In that case, the sleep-deprived brain may be similar to a dreaming brain, in which the internally driven cortical activity were dominant, and this might lead to very vivid, rich conscious experience that is poorly aligned with the sensory input. And our behavior driven by such unaligned conscious experience may also be disconnected from the external world. So this is one possibility. And then the other possibility is if the cortical-cortical interaction, they are not impaired, but the thalamocortical interactions, if the cortical-cortical interactions are impaired, but the thalamocortical interactions are not impaired, remain intact, then the cortical activity will mainly be driven externally. In such case, conscious experience may lose its intrinsic diversity and richness, but we are still able to respond to the external world, although such response may be largely unconscious, and we may be behaving in a more automatic way. And we further hypothesize that these changes in consciousness or in brain function, they may be underlined by the structure changes in the thalamocortical and the cortical-cortical connections, which may be partially driven by the axonal and the myelin plasticity during the prolonged wakefulness. Depending on which of the pathways, whether it's the cortical-cortical or thalamocortical pathway, which of that is more affected, structurally changed, our conscious experience may be biased either towards this dreamlike mode or this blank automated mode. And these changes, myelin and axonal changes, they are likely to be reversible through recovery sleep, which is the mechanism underlying the restoration of the balance between the internally and externally driven cortical activity. So these are the hypotheses that we are testing in this project. And to design the experiments, we look back into the meta-analysis paper. This paper has done this systematic analysis looking into the report on the sleep-deprived consciousness. And these reports shows how severe are different symptoms during sleep deprivation and what sensory domains these symptoms usually occur. And they show that perceptual distortion are very dominant, like nearly more than 90%, nearly 95% of the sleep-deprived patients or participants, they report some level of sleep perceptual distortions. And these distortions mostly occur in the visual domain. So these existing studies show that among all sensory modalities, vision appear to be particularly vulnerable to sleep deprivation. And they also look into how different symptoms of these distorted conscious experience, they onset as a function of sustained wakefulness. And they show that this visual distortion, like there's the altered spatial experience, you may find things being larger or smaller, or the space being entirely distorted. And the visual illusion, which is what they define as you misinterpreting one object as another, and the hallucination, which is you seeing objects or things that are not physically present. All these can start to emerge after 24 hours of sustained wakefulness. And then starting from about 40 hours of sustained wakefulness, we will have distorted thoughts. So this indicates that between 24 hours and 40 hours, there may be a good period to capture the changes in conscious experience using psychophysical paradigm as well as phenomenological paradigm, while our report of conscious experience is still not affected by any potential distortion in our thoughts. So this is why we designed the whole experiment to be lasting 40 hours, the sustained wakefulness, sustained for 40 hours. And the whole experiment is quite demanding for participants as well as for researchers. So it spanned across 3 weeks, including the first week where participants just repeated doing all the paradigms that they were doing in the real experiments to make sure that their performance saturated and to ensure that there's no learning effects in any of the measurements occur during the sustained wakefulness period. And we designed all paradigms to focus on the visual domain following the literature. And what exactly we do is we have participants come in the day one, which is typically a Thursday, and then they take a whole bunch of measures, about 6 hours, including brain structure, brain function, and consciousness. And then they sleep in the institute. And then the next day morning, we take this measure again, and again in the next day evening. And they don't go on, and they don't have any sleep in the next day night. Instead, they just keep doing consciousness measures, and then we take another set of measure in the morning, and then in the evening again. So from the moment they start the measure, like 6 a.m., till the moment they manage to sleep again, like 10 p.m. the day after, this whole entire period is 40 hours. And we take another set of measure immediately after they have the recovery sleep in the institute, and then a few days later, which is typically a week later. So this looks into short-term recovery, while this later measure looks into long-term recovery. And to ensure that participants, they are not napping during this whole sleep deprivation period, they wear a portable EEG headband throughout the study, apart from MRI experiments where they just cannot wear this headband. And in MRI experiments, even in structure scan, we make sure that they are doing some kind of task so that they are not falling asleep. particularly in the structure scan, we give them some movie to watch, but the movie will change the color from color mode to white-black mode at random time points, and they need to detect that whenever the change occurs. So altogether, each participant contributed about 30 hours of MI data and also 30 hours of consciousness data. And then there are roughly 16 participants taking part. Most complete everything, but like 2 participants drop out at some point. And we can still use the rest of the data because we apply a linear mixed effect model to look into the influence of sleep deprivation versus circadian rhythm on brain structure, brain function, and consciousness. So in terms of the detailed measure, we use a multi-compartment MI sequence in the specialized connectome scanner at Kubrick to disentangle the intracellular myelin and extracellular contribution to the MRI structure MI signal. This allows us to separately evaluate myelin thickness, axon density, and axon diameter. So this sequence has clear advantage over a conventional single compartment MRI, such as diffusion tensor image. In these single compartment techniques, they cannot disentangle the contribution of different compartments, like the contribution of axon versus myelin to the MRI signal. So as a result, different changes in brain structure may reflect it as the same changes in MRI indices. For example, an increase in FA value from the DTI measure can either result, a decrease in FA measure can either result from a decrease in myelination or an increase in axon diameter. But these two structure changes, they have functionally opposite consequences in the sense that an increase in axon diameter is typically making the connectivity between the brain regions stronger, or at least making the conduction faster. But the decrease in myelination is having the opposite functional impact. So it's quite important to make sure that we are not combining or confusing different compartment influence on the MI signal, but using the multi-compartment MRI techniques to separate myelin versus axonal contribution to the structure signals. And these compartment MRI, they work in the sense that they can model how the water diffusion, the molecular diffusion of the water molecules behave differently inside the axon versus in the extracellular space versus on the myelin. And it uses different models to capture the different diffusion trajectory of the water molecules in different compartments, and then through which it can estimate axon diameter and axon density. But these are coming from different multi-compartment MI protocols, and they depend on the build of this connectome scanner, which has very high spatial gradient and allow us to separate the microstructure information of the signals. In standard MI scanner, like the typical 3T scanner, we don't have, or even the 7 Tesla scanner, we don't have the ability to disentangle these microstructure indices. So it does depend not just on the particular protocol, like the CHOM protocol or exo caliber protocol. It does not just depend on the particular MI sequence protocol, but also on the MI scanner itself. And to measure the myelin, we use another protocol. So we have 3 protocols involved, looking separately into axon diameter, axon density, and the myelin thickness. And this myelin protocols is looking into how the water proton has different T1 and T2 relaxation compared to the water proton in intracellular, extracellular space have different relaxation T1 and relaxation T2 compared to the water proton in the myelin, and using that difference to disentangle the myelin versus the myelin water versus the intracellular, extracellular water contribution to the signal, and then estimate the myelin water fraction. These are the measures which allow us to look into the structure changes in the thalamocortical connections and the cortical-cortical connections. But the exact reason why we are able to connect to the external world is not just due to the fact that there is this structural connection between cortex and the external world through thalamus, but through the exact topology of this connection. And the thalamocortical connections, for example, the connection between thalamus and the primary visual cortex follows a topographic organization. This means individual neurons in thalamus project to a very limited set of neurons in the primary visual cortex. And these neurons are typically spatially adjacent rather than scattered across the surface of primary visual cortex. And then adjacent neurons in the thalamus project to adjacent groups of neurons in primary visual cortex. It is through this almost one-to-one like topographic projection that allowed different sensory stimuli to evoke different patterns of activity in primary visual cortex and effectively linking the brain and the consciousness to the external world. So for example, these voxels in primary visual cortex will only respond to this limited range of locations in the visual field, while this voxel will only respond to this limited range of locations in the visual field. If the thalamocortical connections become weakened and become sparse, then clearly we will lose the connectivity, the connectedness between the brain or consciousness and the external world. In this case, sensory stimuli may even fail to evoke cortical activity. But it's not just that when the thalamocortical connection becomes sparse, that we will lose connectedness to the external world. It is also when the connection becomes overloaded, becomes too dense, almost like an all-to-all connectivity pattern. When that occurs, we will also lose the connectedness to the external world, because in that case, whatever sensory stimuli you receive, they may end up evoking identical patterns of activity in the primary visual cortex. So this topographic organization is extremely sensitive. When it has a net decrease or when it has a net increase, it is likely to be disrupted, effectively leading to a disconnection between the cortical activity and the external world, and thereby a disconnection between the consciousness and the external world. So to evaluate this organization of thalamocortical connection, clearly we don't have the resolution in terms of the structure measure, but we can still use functional measure, in particular population receptor field measure, to estimate the topographic organization of thalamocortical connection from the functional perspective. So this is one measure we took. And then this measure can tell us how the topographic organization of the connection is influenced, but we also want to know how the interactions, thalamocortical interaction as well as cortical-cortical interaction is affected by sleep deprivation. So we use 5 different fMRI paradigms, and they involve different level of sensory richness and the cognitive demand. We also applied both univariate connectivity analysis and the multivariate connectivity analysis, all these methods together to evaluate whether the thalamocortical interaction or the cortical interaction or both is affected by sleep deprivation. One of these paradigms that we used is a face house discrimination task. In that task, participants, they need to discriminate face house, and we change the signal to noise ratio of the stimuli so that we can effectively dissociate their conscious experience from the stimuli itself. And then this paradigm allows us to evaluate whether the regional activity pattern correlates stronger with conscious experience or with sensory stimuli, and we look into how this correlation between the brain activity and the conscious experience versus sensory stimuli changes during sleep deprivation. So these are the brain functional measures. And then when it comes to consciousness measures, we applied different perceptual discrimination paradigm. For example, the temporal discrimination paradigm, where they need to be able to even discriminate whether it's a single flash or 2 flash on the screen. and the spatial discrimination paradigm, where they need to discriminate whether the two lines are aligned or one line is left versus right word offset compared to the other line. And then the orientation discrimination paradigm, where they need to discriminate small difference or small change in orientation. And then finally, the space house task, where they see a very noisy image. The noisy level, currently, the image I'm showing here have a middle level of noise, but the noise can become really significant. So it becomes really noisy, and they still need to answer whether there's some face or house in the noisy image, or it's just a pure noise. So these different paradigms allow us to evaluate the level of alignment between conscious experience and the external world. And that is basically evaluated from the accuracy of their answer. And we do that for different sensory signal strengths, noise, and different level of ambiguity. And then we also use in these paradigms, the stimuli are presented for a very short duration, typically a few milliseconds. And we also use paradigms where the stimuli are presented for as long as needed, and participants just need to respond as quick as possible. So we use these paradigms to evaluate the temporal lag in alignment between conscious experience and the external world under different levels of cognitive demand. In addition to these perceptual measures, which allow us to evaluate the degree of misalignment between conscious experience and the external world, we also use metacognitive measures. The reason is, in these perceptual measures, participants, they just give a perceptual response, but we don't know the degree to which the perceptual response is a true reflection of their conscious experience, or whether it's just they are making errors, or they are just simply guessing. So in addition to the perceptual measure, we also ask them to give a confidence rating about how confident they are in the degree to which their perceptual answers reflect the physical stimuli. And we use the confidence rating to evaluate whether their perceptual answer reflect their true conscious experience, or whether it's a pure guessing, through which we then estimate whether the misalignment between perceptual response and the sensory stimuli is due to true distortion and hallucination, or whether it's simply due to guessing or errors. The idea is, if the confidence rating they give in these correct trials are not different between sleep deprivation and the well-rested state, but the confidence rating they give in these incorrect trials are higher, then it indicates that in these incorrect trials, what they are reporting is truly their conscious experience that are misaligned with the external world. So we use that information to tell whether their perceptual response are truly genuine reflection of their consciousness, or whether it's pure guessing or errors. In addition to that, we also use phenomenological measures, that is through interviews or questionnaires, to evaluate if there are any distorted or hallucinatory features in their conscious experience. And I think the most interesting and the telling part come from these phenomenological measures. And I'm just taking some examples of these. So this comes from one participant saying everything happens with the fixation cross during sleep deprivation. Sometimes they see it as a face, other time it looks like a cap. And then at one moment, they see like 3 cartoon characters, just outline, spatial outline of these characters fighting with one another near the fixation cross. And these are entirely new experience to the participant. So the participant didn't recognize these characters, but they are enjoying this kind of hallucinatory experience. And this comes from another participant who is reporting during the experiment when they are doing the face-house discrimination, where they need to answer whether it's a face or house or pure noise. They start to see an apple out of this image, and then they find themselves not in the experiment room anymore, but in a field watching the apple falling out of the tree. And this happens quite frequently for this participant. That is why they report saying that they think they are going in and out of their consciousness, like switching in between being in the experiment room and not in the experiment room. But they say that this is not exactly like dream. It's entirely random. So it's like they do the experiment for about 10 minutes, and then they will be getting out of their consciousness for a few seconds. And when that happens, they are aware that they are out, and then they are also aware that they are back in the room, in their conscious experience of the room again. And in addition, this participant also report that thoughts would pop into their mind, and it will lead to some kind of dreamish feeling. It's like dreaming, but being awake. In addition to having this very vivid hallucinatory experience, like feeling this hallucinatory objects or hallucinatory things is as vivid as real things, participants report their experience of the real world is actually potentially less vivid than what they typically experience in a well-rested state. So the hallucination becomes more vivid, but the physically induced experience become less vivid. They even report a clear sense of disconnection from the external world. Like this participant saying, they feel that they are kind of awake, but not exactly awake. So they feel that they know what is happening there, like everything is on the screen. They experience that, but they just don't feel they are very responsive. It's possibly a bit like this lock-in syndrome kind of feeling, like they are a bit paralyzed. And this is another participant who report perceiving themselves from the third person perspective. And comes from then again, another participant who just report that there feels a lighter boundary between what is real and what feel like less real. So these phenomenological reports show that there is a sense of disconnection from the external world, but there is not just a sense of disconnection, there's actually real disconnection, which we can tell from the psychophysics experiments. Here is the result from the face-house discrimination task showing how the psychometric function shifted from the well-rested state to the sleep-deprived state. What is quite interesting is you can see that in this task, it's a 3 alternative false choice where they say whether it's a face or house or a pure noise. So the chance level should be a third, like 33%. But when there's only noise on the screen, like when the signal to noise ratio is 0, participants actually get less than the chance level. It means they are actively seeing noise as face or house. So they are just not making guess, but truly seeing noise as something. And that is how they can have this less than chance level accuracy. This is one interesting observation. And the other is even when the signal to noise ratio is 1, like there's pure signal, no noise, there will still be some level of misalignment between their perceptual response and the sensory stimuli. So the psychometric function saturates below 100% accuracy. And there's also a general shift in the discrimination threshold, like from a lower one to a higher level. This just means this misalignment between perceptual response and the sensory stimuli gets more significant when the signal strength is weaker and the noise is stronger. So this is the perceptual measures, but from the metacognitive measure, looking at how the confidence rating changes, we can see that this part is the sleep-deprived part. This middle part, there is not so much change in the confidence for these correct trials where they perceive face or house as face or house, or where they perceive noise as noise. But there is a clear increase in the confidence for these incorrect trials, particularly for the false alarm trials where they see face or house out of noise, like increase from 2 to nearly 2.75. They are rating between 1 and 5 in terms of the confidence rating. And there's also an increase in the wrong association trials where they perceive face as house and they perceive house as face. And there is also some increase, but to a less degree in these mistrials where they perceive face or house as noise. So this increase in elevation in the confidence rating in these incorrect trials, coupled with unchanged confidence in the incorrect trial, indicate that there is a true misalignment between consciousness and the external world, rather than people just merely guessing or making incidental errors. So these are the results from the psychophysics measures, and then from the fMRI measures, we also have this face house discrimination task, very similar to the version outside the scanner, but the only difference is we don't get a confidence rating inside the scanner due to the time limit and due to the way how we analyze the data. So inside the scanner, there's only the perceptual measure. But from the perceptual measure, what we do is for individual brain region, we calculate the differentiation in spatial activity pattern between every two pairs of trials. And we calculate this as 1 minus the correlation in the spatial activity pattern. And then we divided these different pairs of trials into 4 categories. One is these 2 trials, they have the same stimulus category, like they may both involve a face stimuli. And also they have the same percept category. It means participants report face for these 2 trials. And the type B is these 2 trials have different stimulus category. It might be one trial is a face stimuli and the other trial is a noise stimuli. But participants give the same perceptual answer. They report face for both these trials. And the third category is the 2 trials have the same stimulus category, but different percept category. Like they may both involve the face stimuli, but in one trial, participant report seeing face, while in the other, they report seeing house. And then the last category is the 2 trials have both different stimulus category and a different percept category. So we divide the pairwise trials into these 4 categories. And then the last step is we quantify the change in the differentiation of regional activity pattern from these type A or type C trials. These are the trials where the stimuli are the same between the 2 trials, to type B or type D trials. So these are the trials when the stimuli is different between the 2 trials. So by looking to this, we are effectively evaluating the correlation between brain activity pattern and the sensory stimuli. And then we also look into how this differentiation in brain activity pattern changes from type A or type B trials, which are the trials that they report having the same percept category, to type C or type D trials, which is they report having different perceptual experience. So these are the trials. From looking at this, these allow us to evaluate how the brain activity pattern correlates with conscious experience, or at least with their perceptual report. And finally, we look into how this differentiation in activity pattern trend from type B trial, which is where they have different stimuli but same percept, to type C trial, which is they have same stimuli but different percept. So looking to this allow us to evaluate whether the differentiation correlate more strongly, the brain activity pattern correlate more strongly with stimulus or with perception. So these are what it allows us to identify for individual brain region, whether it's reflecting more the stimuli or whether it's reflecting more the sensory conscious experience. And here is how the result look like. So this is the change in the differentiation in regional activity pattern from the trials where we have the same stimulus to the trials where we have different stimulus. And the value here is the t value. So a larger value indicates that this brain region is able to differentiate different sensory stimuli better. So this value effectively evaluates the correlation between regional activity pattern and the sensory stimuli. As you can see in the well-rested brain, the posterior region, like V2, V3, and V1, as well as the frontal region, particularly like region 9 and the 46 Bracco areas, they all have quite high differentiation towards the different sensory stimuli. So they have a high correlation with the sensory stimuli in this sense. But in the sleep-deprived brain, this ability to differentiate sensory stimuli clearly decreases. From in the well-rested brain, it has a quite high t-value, nearly 36, and this is because we are analyzing the data on a trial-by-trial basis. To the sleep-deprived brain, it has a much lower t-value, and this decrease is very significant in posterior region, even more significant than in the frontal region, because you can see in the frontal region, these parts still have a high ability to differentiate, while in the posterior region, it now has a weaker ability compared to the frontal region to differentiate sensory stimuli. So this shows that in the sleep-deprived brain, the frontal region have a higher correlation with sensory stimuli than the posterior region, while in the well-rested brain, they have similar level of correlation. And generally speaking, from the well-rested to a sleep-deprived brain, you have a decrease in the correlation between brain activity and the sensory stimuli. Now we look at the correlation between brain activity and the perception from by looking at the change in the differentiation in brain activity pattern from these trials where they report the same percept category to these trials where they report different percept category. And we can see that comparing the sleep-deprived brain and the well-rested brain, there is first a general increase in the correlation with the conscious experience. And this increase is particularly strong in posterior regions, particularly those visual cortical regions. So finally, this is the most interesting part. We compare the change in regional differentiation from the type B trials, where it is between these two trials, there's different stimuli, but the same percept, to the type C trials, that is between these two trials, there's same stimuli, but different percept. So if there is an increase in the differentiation in regional brain activity from type B to type C trial, then it indicates that the differentiation in the brain activity is a more reflection of stimulus rather than, if there is a decrease in the regional differentiation pattern, it indicates that the differentiation in the activity of the region is more a reflection of the stimulus rather than percept. This is why the region shows higher differentiation in these type B trials, where there's different stimulus, than in these type C trials, where the stimulus is the same, but percept is different. By contrast, if the differentiation pattern shows an increase from type B trials to type C trials, then it indicates that the regional activity pattern correlates stronger with perception than with stimulus. This is why the differentiation will be stronger in these trials where they have the same stimulus but different percept than the trials where we have different stimulus but the same percept. And the interesting part is we see a reversal pattern from the well-rested brain to the sleep-deprived brain. In the sleep-deprived brain, almost the entire brain, apart from thalamus, shows a higher correlation with the percept than with the stimulus. This is how the whole brain shows an increase in differentiation from the type B to type C trials. And this is particularly significant in posterior region. But in the well-rested brain, the whole brain, including thalamus and every part of the brain, shows a decrease in differentiation from the type B to type C trials. And this does not necessarily mean that the well-rested brain is not responding or is not correlating to conscious experience, but it could just mean that the perceptual answer participants give in the well-rested state may largely be guessing. So the perceptual answer, like here, is very noisy, and you can consider the type C trials not as the trials where they truly have different perception, but the trials where they are purely guessing. So it might have same perception or different perception. While the type B trials is the trials where they have different stimulus, but again, the perception could also be guessing. So the pattern here is to a large degree in the well-rested brain indicate the level of the correlation between the differentiation in the individual regional activity pattern with the subliminary or subthreshold sensory stimuli, like whether this brain region is capable of differentiating the stimuli when it is below threshold. And this pattern can be indicated, can be thought to indicate that the frontal regions have a very high ability to differentiate the stimuli when it is even below threshold, below sensory threshold, more so than the posterior region. So this interpretation of the well-rested brain will be slightly different from the interpretation of the sleep-deprived brain. But in any case, in the sleep-deprived brain, it is very clear that the whole brain is correlating more strongly with perception than with stimulus, particularly the visual cortical regions. So these patterns shows the regional activity differentiation on a region-by-region basis. But in addition to that, we applied the connectivity analysis, the multivariate connectivity analysis, to look into how different brain regions correlate in their differentiation, which allow us to evaluate whether a change in the activity pattern of a region is associated with a change in the activity pattern of another region. The way we do that is we first calculate the differentiation in activity pattern between time-wise time points for individual brain region. And from this, we can derive a time series of the differentiation in activity pattern. In this time series, the x-axis is basically pairwise time points, while the y-axis is the level of differentiation. And then we look into the correlation between different brain regions in this time series of spatial differentiation. And that is a measure of multivariate connectivity, capturing whether a change in the activity pattern of region A is associated with a change in the activity pattern of region B. If this multivariate connectivity is low, it means, for example, between time t1 and time t2, region A is showing a difference in activity pattern, but region B is not showing any difference. Like region B may have identical activity pattern between the time point T1 and T2. And conversely, between the time points that region A has same activity pattern, region B may have different activity pattern. So this is what a low level of multivariate connectivity indicates. In addition to this, we also apply conventional univariate connectivity. That is basically you use the mean activity across all voxels to represent the activity of a region, and you use that to look into whether a change in the mean activity of a region is associated with a change in the mean activity of another region. And these two connectivity can allow us to probe into a potential change in the topology of the connection. This is particularly the case if we see an incongruent change between univariate connectivity and the multivariate connectivity. So for example, if the thalamocortical connection is changing from its default topographic organization to a all-to-all connected pattern, a very diffusely connected pattern, we would expect an increase in univariate connectivity, but a decrease in multivariate connectivity. In this case, it is because whatever activation you have in the thalamus is likely to induce an activation in the primary visual cortex due to this increased connectivity between them. However, the same activity pattern in the thalamus may induce different activity pattern in the primary visual cortex because their connectivity become more diffuse. It's like at one time point, this thalamocortical neuron may activate this neuron in primary visual cortex. At another time point, this thalamus neuron may activate a totally different neuron in the primary visual cortex. So you would expect an increase in univariate connectivity, but a decrease in multivariate connectivity. And on the other hand, if the connection between thalamus and the primary visual cortex is simply become more sparse, then we would expect a decrease in univariate connectivity. It's like the thalamus activity is less likely to evoke an activity in primary visual cortex. So this is why we use both. This is the reason why we use both univariate connectivity and the multivariate connectivity. And we apply the connectivity analysis to 5 different fMRI paradigms. These involve paradigms that is really simple. It is both cognitively simple and sensorily simple, like this psychomotor vigilance task where you have a very small number counter, roughly the size of the fixation cross. It is minimum sensory stimulation, and it will show up at random time points, and you just need to respond whenever you see the number counter. So this is very simple. To this population receptor field mapping experiment where the cognitive task is very simple, very similar to the psychomotor vigilance task, where people will just need to detect the random change in the fixation cross color. But the sensory information is much richer. It is a high contrast stimulus moving across the entire visual field. And then we also have these paradigms where it's cognitively demanding, like people need to do attentional capture task or some kind of visual search task. They need to find the diamond shape and answer whether it is a L or R inside. But it is sensorily quite simple. The stimuli has very low contrast, and it is also very small in size, not as large as the retinal topic or as the population receptor field experiment. And we also have the experiment that is cognitively demanding as well as sensory rich. This is the face house experiment. And the participants in the post experiment interview we have with them, they report this experiment, this face house experiment, being the most difficult one compared to all the different paradigms we used in the fMRI or in the pure consciousness measure. This is because they say this paradigm is extremely ambiguous. They find it very difficult to make decision. The decision making in this experiment is very difficult. And for that reason, they find this one most demanding. All the other paradigms, the decision making is not ambiguous. It is a clear answer, but this one, they find that they not just need to make an answer, but they need to kind of have the criteria for making the answer, and that is why it's particularly difficult during sleep deprivation. In addition to all these paradigms, we also have the eye-open resting state that is also sensorily simple and cognitively simple. People may be having mind wandering, but it's not involving any interaction with the external world. So this is why we define that as cognitively simple. And we apply the univariate and the multivariate connectivity analysis to individual paradigm to access the thalamocortical and the cortical interaction. And we do that for different brain pacillation scheme, like the fine pacillation, dividing the brain into more than 200 region per hemisphere, or the coarse pacillation, dividing individual brain region, dividing individual hemisphere into roughly 40 regions. And we also use retinal topic pacillation, just pacillate or single out all these visual cortical areas, like these retinal topical areas, roughly 22 areas per hemisphere. And due to the limitation of the space, I can only show the result from the coarse pacillation and the retinotopic pacillation, because otherwise it cannot show in the whole screen from these 200 regions. But they are roughly consistent. It doesn't depend on the pacillation scheme. So what is shown here is the change in connectivity, the multivariate connectivity from the well-rested brain to the sleep-deprived brain. And a large value here, this is the t-value. So a large t-value, a positive t-value indicates an increase in connectivity, while the negative value indicates a decrease in connectivity. And as we can see here, the connectivity within the posterior cortex, particularly the visual cortical region, they show a substantial increase, very large. And the connectivity within the frontal cortex also show an increase. So these are the frontal region, but to a less degree than that in the posterior cortex. The connectivity between posterior cortex and the frontal cortex remains largely unchanged. The connectivity between the subcortex and the frontal cortex, like the subcortical region and the frontal cortex, so it's here, frontal cortex, subcortical region, they are also on average relatively unchanged. But the connectivity from subcortical region, in particular from the thalamus and the brainstem region, to the posterior cortex. So it is the part here, the connectivity between thalamus and the posterior cortex, they show a very large decrease. So this is the overall pattern. But the interesting thing also is when we compare this multivariate connectivity with, with this univariate connectivity, we show an incongruency here. So the univariate connectivity, as you can see here, between V1 and the thalamus is increased from well-rested to the sleep-deprived brain. This is the pattern of univariate connectivity while the pattern of the multivariate connectivity, as you can see here, is decreased. Apart from this connectivity between V1 and the thalamus that is incongruent between uni and multivariate pattern connectivity, the rest of the pattern is roughly consistent between uni and multivariate connectivity. So this is one interesting pattern. And the other interesting pattern is the connectivity change within the frontal cortex is task dependent, while the connectivity change within the posterior cortex is not. So this is the face house task that is cognitively demanding and sensory rich, and we can see a clear increase in the connectivity within frontal cortex. And this is the population receptor field mapping task that is sensory rich but cognitively simple. We also see this increase. And this is the attentional capture task that is cognitively demanding but sensorily simple. We also see this increase. But in the psychomotor vigilance task, which is cognitively simple and also sensory simple, we don't see this increase in frontal cortex in terms of the connectivity. Like the connectivity from the sleep deprived, from the well-rested brain to the sleep deprived brain is roughly unchanged in the frontal cortex, but the connectivity within the posterior cortex is changed. And similarly, for the purely eye-open resting state, the connectivity within the frontal cortex is roughly not changed, but the connectivity within the posterior cortex has changed a lot. So in these patterns together, they show that there is a robust change. Sorry, the slides are a bit slow. But together, these patterns show that there is a robust change in the connectivity within posterior cortex. It shows a substantial increase from well-rested to sleep-deprived. There is also a robust change in the connectivity between the thalamus or brainstem region and the posterior cortex. It shows a decrease, but this is apart from primary visual cortex. And then there is also a robust change in the there is a robust lack of change in the connectivity between the frontal cortex and either the posterior cortex and the subcortical region. And I think for some reason, the slide is extremely slow. So if you don't mind, this is a high resolution version of the slide. I can change to the low resolution version to see if it might be better.
So Chen, we're just at 12 o'clock now.
Oh,
So
yes.
I'm wondering whether it makes sense for us to switch into question, because
Sure.
otherwise we don't want to leave no time for you to get
So
discussion.
Sure, and I have almost finished talking to the empirical part, so it's just a few more slides. Let me just get in this one. Let me just use, I don't know if that's the reason why the screen is slow or whether it's because the computer itself is slow. Yeah, it's possible that it's just the computer itself is slow. I don't think it is making any change, but let me just continue here because I know the time is up. So these are the robust changes, but there is also the change that is different between multi and univariate connectivity. That is in terms of the connectivity between V1 and the thalamus. It's increase in the univariate connectivity, but decrease in the multivariate connectivity, indicating a potential shift in the topographic organization. And then this connectivity within frontal cortex is task dependent. So these are the non-robust change. And consistent with this hypothesis of a change in the topography of the connection, we find from the population receptor field experiment that in the non-sleep deprived condition, individual voxel in the primary visual cortex is responding to a limited range of locations in the visual field. Like you can see here, this voxel is responding to here, this voxel is responding to here, and the adjacent voxel is responding to adjacent location, suggesting a topographic organization. But in the sleep-deprived brain, individual voxel is responding to a very diffuse range of locations, a very scattered range of locations, and adjacent voxels may respond to very distant locations. So this is congruent with the idea that the connection between thalamus and the primary visual cortex lose this topographic orderliness. And finally, we find from the structure data that I don't have the time to go into detail today, but we find from the axonal measure that there is a general increase in the axon diameter. This is particularly significant for the thalamus and particularly significant for the connection between thalamus and the primary visual cortex. And this is consistent with the idea that the connectivity between the thalamus and the primary visual cortex may be increased, but the net increase may be associated with a loss of topographic orderliness. And to sum up, what we show is in the sleep-deprived brain, the cortical interaction is relatively intact, and it even show an enhanced integration among posterior cortical region. By contrast, the thalamocortical connections, particularly those linking the thalamus and the posterior cortex, it is disrupted structurally, topographically, and also functionally. And because of this disruption, this disconnection between thalamus and the primary sensory cortex, it effectively leads to a decoupling between cortical activity and the sensory stimuli, which is potentially related to the misalignment between conscious experience and the external world. But participants are not necessarily aware of this alignment. It depends on how much they have the idea of the real world is like, which is why they are aware of this misalignment in the experiment, like in the hallucination experience, like they see something out of the fixation course because they know that in the experiment, it should be a fixation course rather than these hallucination figures. But they are not aware of this misalignment in the experiment, like face house experiment, where they know that it can either be a face or house and pure noise. And in these cases, because they know it can be either one of these, and when the hallucination happens, mixed with the fact that it can either be one of these three scenarios, they cannot metacognitively tell whether which are the trials where they are hallucination versus which are the trials where they are truly perceiving the physical stimuli. And then we also find that in a well-rested brain, it's able to maintain the delicate balance between the interaction, cortical-cortical and the thalamocortical. In particular, the frontal cortex of the well-rested brain seem to be able to respond to subthreshold stimuli, potentially supporting unconscious monitoring of the environment. And this ability is lost in the sleep-deprived brain. From this perspective, the well-rested brain is well-suited for both consciousness and for intelligent behavior. That means your adaptive interaction with the external world. But the sleep-deprived brain retains mainly the capacity for consciousness, which again indicates that consciousness may be a more fundamental function of the brain. So that is all the part related to the empirical study, and the other part related to the integrated information theory. I don't mean to expand the theory, but I just want to clarify some potential misunderstanding or the reasoning behind the theory.
So Chen, we're now. I worry that if you go on to do that, we'll not have any time for questions.
Sure. Yes, let's have the question first.
Okay, I think that's a good idea. So let's just stop. Well, first of all, we should thank you for a very rich and fascinating talk. Thank you very much.
Thank you.
And let's stop the record.